Greeting Earthlings, if you follow the channel, you know that we are resurrecting the Apollo communication system with original spacecraft and NASA ground equipment. In the last episode, we admired and hooked up our UDL box, short for Updata link. It should allow us to receive digital commands sent from the ground, decode them, and send them to the appropriate system in the spacecraft. We got it to receive some bits, but they did not look quite like what they were supposed to be.
Got it.
Okay, so we have bits.
Genuine bits.
Excellent. Can we check we got the right ones?
I think the polarity is inverted.
No, I think we have 00100 first, the narrow one.
This would mean that it's switching to the different subbit encoding
Yeah.
after only 2 bits.
Yeah.
And I'm expecting to see 3 bits.
I mean, we should never get that many ones in a row. So something's definitely messed up.
Something appears to be wrong. We are going to try to figure out why in this episode. Okay, so we're receiving something, but not quite sure.
But our vehicle select output's not going active.
Right.
So
Yeah.
Oh, you checked that?
yes.
Yeah.
Okay. Alright, so let's fix that first. So every message starts with a 3-bit pattern, which defines the vehicle address that the message is targeted to. Assuming I am sending the proper address for the command module, which should be 4, our UDL should immediately decode that the message is addressed to itself and activate the vehicle select output. But Mike just checked it, and unfortunately our UDL does not even think it is addressed. There are so many things that could be wrong. First off, the bits are not transmitted as is, but are instead encoded as a pattern of 5 subbits. A 5-bit pattern is used for the ones, and another one for the zeros. If we had the wrong subbit pattern, that could prevent address decoding. On top of that, the subbits are further encoded on an audio carrier using phase shift keying, or PSK. Sadly, part of the PSK encoding circuit was missing from our undocumented Updata transmitter, so we had to take a stab at re-implementing the missing parts in episode 18. I could certainly have done this wrong. Anyhow, we know for sure that we have an issue very early on, within the first 15 subbits. Naturally, we first suspected our re-implementation of the Updata transmitter missing circuits. Okay, we think we might have found a problem. This is the signal we are getting from the encoder, the Updata box, and that's the PSK signal, and we should get something like that, and it's not quite the same. And Ken, you think you found the issue?
Yeah, I made a little JavaScript simulation so I can try different experiments, and I think the problem is a phase shift. So I can put in some subbits, some ones and zeros, and what we want to get out looks like this.
So it looks like the NASA drawing.
And you'll notice that the peaks and the bottoms are all in a nice line. If we make a little phase shift between the two signals, now you can see we get some distortion, and we lose our baseline here. It's shifted up for the 0 bits, which is just what we see on the oscilloscope.
We had noticed that our transmitted PSK signal in red here was close but not quite what it was supposed to be. A subtle mistiming of the phase shift location could certainly cause that. And you can actually see that the yellow 1 kHz is a little bit out of step with the blue 2 kHz. It's slight, but might be enough to screw us up. I suspected right away one of the resonant filters that I had implemented. The phase shift is not happening at the right place. It should happen right in the middle, I think.
So it's a fairly small phase shift of 35 degrees, but it's enough to mess up the signal and match what we see on the oscilloscope.
So I think my problem was on this card over here, which is not an original NASA card. I had replaced the stuff that was missing by my own stuff. And I went back to what I had done. I was tuned to 977 Hertz, so I'm 22.5 Hertz off, which doesn't sound like much. In a very high Q resonance circuit like we have here, the slightest detuning will cause a notable phase shift. I was just 22.5 Hz off, but that was enough to phase shift the 1000 Hz reference signal. And so I had to retune the 1 kHz filter so it's centered, so it sprouted a few more capacitors. But now I think it's centered at 1000 Hz. Turn it on. And I send some data. Here's my data. Get this a little bigger. Yeah, you can see it. So now my 1 kHz is correctly tuned, and the zero crossing corresponds with the phase shift, and I have something that's a lot closer. Actually, it looks exactly like what I should get over here. So hopefully that'll fix it. Hello 13, this is Houston.
We hear you.
Okay, so we have that, and I don't have the modulation going yet. Okay. You got something?
We stopped getting a bunch of noise.
Okay, so that's
That's
good.
a sign.
So, okay, that's 0. Okay, so that's one command. I can't remember what it is. 4, 6. Can you see?
These are subbits.
Okay. Okay, we are making slow progress. The next step is to compare the subbits we sent with the subbits we received. If they match, we'll have at least gotten the PSK modulation correct. Okay, now I have a long cable running all the way from over there back to here so we can compare what we send with what we receive. And so far the result is pretty darn good, I would say. And the signal is distorted because of the long coax cable. And it looks like we're decoding our signal okay. So I would call that partial victory. We are modulating PSK, getting it all the way through the microwave link, getting it back down, and it's getting us the same thing. If we did a little bit better setup, we would see a square wave. But so far, I would say it completely matches. But you are not decoding. Am I on the wrong ship?
You might be sending the wrong preamble.
I am sending 460100. So what we're looking for is whether it triggers a recognition, right?
Right.
Don't. You get it?
Should be triggering it right now.
So I think we need to manually decode it and figure out what we got. Alright, we are one step closer. We can send subbits across the link and recover them exactly. Unfortunately, our UDL receiver still didn't seem to decode the address preamble. We need to call in Master Ken to rescue us and see if he can decode it manually.
So what is it supposed to be sending?
So it's 46, then 070, and I can't remember what that command was supposed to be.
No, so 4607 should be 11011 at the beginning, so it looks like it's not right from the beginning.
No, that's not 110.
So it's an encoding problem?
Well, the data we're receiving doesn't make any sense.
The encoding could have been changed.
Because wasn't that box modified for
Yes.
the program?
Yes.
It's also a black one box, and this is a black two.
Yes. So we might not have the right encoding. So what have you guys figured out?
So I'm looking at the schematic I reverse engineered a few years ago for the subbit generation.
Way back when in episodes 9 and 14, when we still didn't exactly know what our mysterious Updata transmission box full of mysterious Motorola circuits actually did, Ken spent several months reverse engineering its tangles of wires and came up with the schematics of the beast.
And what I'm noticing is that what I thought were the subbits for the vehicle address are basically what we're seeing on the scope and don't match the documentation.
So the box is acting correctly as it's
hardware designed.
implemented, but it's not
It's incompatible.
It's not a block 2 whatever Apollo thing anymore.
Right. So there's a contradiction here between what we see, what the circuit does, and what the documentation says it should be doing.
And Mike dug into its secret papers and found the answer.
This is the functional integrated system schematics for spacecraft 008. So if we look right at the beginning of this diagram, there's our Updata link confidence test set with 2A17, which we have as a sticker on the front of that box. So if that wasn't the box, you know, it is the right kind of box for the test. But this is all block 1, right? So that box was built for block 1. And we have a block 2 Updata link.
We also checked out, we have schematics for a UDL.
Yeah, we have schematics for a UDL. It doesn't explicitly state in this document if it is a block 1 UDL or a block 2 UDL. But it does give dimensions for the UDL at the beginning of the document, and those dimensions don't match block 2. So presumably, this is for block 1. The logic in the top left here, this logic here is doing the decoding of subbits. And if we map out this logic, it agrees with the subbits we're seeing from the test set. So it seems like probably that this is a block 1 versus block 2.
It's a block 1 coding on the transmitter and a block 2 decoding on the receiver.
Yeah, it might not be too unexpected for the subbits to change here. We've used this document as a reference a few times, the proceedings of the S-band technical conference. It shows the subbits, and the subbits shown in this diagram match neither the block 1 or any other documentation we have.
Oh, really?
So this is a third set of subbits, yeah.
Okay. So the theory is that we have the wrong subbit encoding on our transmitter.
Yeah.
But we can change that.
You just need to open up the box, pull out some modules, cut some traces, connect some wires, and we should be good to go.
But before we do that, we're going to test it because I made a special box for that with my HP equipment. I made an HP UDL. Yes. And then we can try the pattern and be sure that's the problem.
Yeah, before we make any modifications.
Right. So here is my HP version of the UDL. I have this source that has 2 oscillators, that's the 1 and 2 kilohertz, and I can modulate the 2 kilohertz with BPSK, and I modulate it with a stream that comes out of the serial generator. I can do any bit pattern I want, so let's do 111 0 0 0 111. I have to load it and tune. There you go. 111 0 0 0 111, and I can try a different subbit encoding. So I'm going to go 101 load. There you go. And then I can make it as long as I want. I can enter manually a full message and see if it's getting decoded. Okay, so I think I have programmed the correct bit sequence for block 2. We're transmitting it. Do you get anything on the receive side?
We see the data coming in, but we don't get a pulse that would indicate that it interprets the vehicle code. So it doesn't recognize that preamble, the vehicle code.
Oh, we have a fail. We might have polarity inversions and all that good stuff. Did I do the bit in the right sequence? Because I have 11011, that's here, so I have a 1. And then I have 0, which is 00100, 00100, and another 00100. But is it little Indian or big Indian? Which comes first?
I assume it'd be.
I believe it's beginning, yeah.
Should we try the reverse?
I think we should try inverting it first.
So I can get 0 0 1 0 0, and then here I invert this one 1 1 0 1 0. So I flip my bits and will work. and I'll just send it to you.
Nope.
Didn't do a thing.
Yeah, I can see the bits are in there in the reverse order, but we're not getting a pulse on channel 2.
Okay, so then we might be reverse on the data itself, which I can do here. So if I get here, I'll change the order of my bits. Did that do anything over there?
It did flip it over, but you still have the
So
reverse vehicle code.
I'm flipped over now. Well, so at least my emulator is working. You're receiving the data, right?
Yeah.
So now we have to find what the right message is. Is there a subbit error pin or something that we can get that confirms it has received something? Or is it time for lunch? Oh no, the old thing is resisting us, changing the coding to match the documentation, or at least one of them, and trying all different bit orders and polarity permutations is not working either. We then decided to try a different approach to discover the proper code. Why not send it some pseudo-random noise, which my HP generator can do, and see if we can trigger it by accident. And now it has noise.
And you can see the noise here too.
Okay. Oh, it's not a noise. Okay, and now we see it triggering on the vehicle address when the noise gets it right.
Yeah, so there's
this
random
is-
noise that's triggering it.
This is sort of scary, just we would...
I agree.
And then you just think on that, and we're going to try to reverse engineer see what bits trigger that.
Exactly.
And to our surprise, it worked. Kinda, sorta. It actually worked way too well. We could trigger it way too often, as you can see in the green trace. Worse, the trigger patterns were not reproducible. This got us into further head scratching and sent us yet in another direction. So I can send it some pseudo-random stuff, and it does trigger the recognition, address 4, whatever we wire it to. But the pattern before it is not consistent, and we were puzzled until we discovered that we probably had one wire not connected properly.
Right, yeah.
We were looking for the reset condition.
Right, yeah. So we're trying to understand what happens when bad subbits are detected. How does that reset the subbit detection? How does that reset the bit detection, right, of your vehicle code and all of that? This is a shift register that is the current subbits. So there's 4 registers, and then the inputs to the first bit are also used, so that's your 5 subbits. As groups of 5 subbits are translated into bits, those bits are put into this register decoder. The first 3 bits of this are used both for vehicle detection and system detection. So what we're looking at is these first 3 bits, being 100, will trigger the address 4 wire, which is what we have up on the scope.
That's the green trace.
That's our green trace. So the UDL is programmable by wire to pick what your vehicle code is going to be. So there is a pin for each of the 8 different possible vehicle addresses, 0 through 7. So we have a loop back on our harness.
That's the little white wire?
This wire down here that we have this
Right.
before. So the idea behind that is you pick off which of the 8 different vehicle addresses you want to be, and run it into the V pin, which will set the vehicle flip-flop. So if we look at the pin out for the connector, we have external control A0 through A7, and then external control V. So we figured out, if we want to set our address to 4, we wire up A4 to V and leave the rest of them disconnected.
Right.
That was where we got to.
And that's what we did, and we thought it was good, and we went to lunch.
Yep. So while we were puzzling out, how does this error detection work, Eric noticed that there are inputs to the first 3 bits of the bit register, A prime and A double prime.
One sets them all to 1,
A
one sets them all to
prime
0.
sets them all to 1, and A double prime sets them all to 0.
Which is very bizarre.
Yeah, it was very weird, and we didn't understand why that would be, and also didn't immediately know where A prime and A double prime were connected to. But looking over here, these 2 little A17 gates here, these two gates detect both of the possible types of errors with your subbit detector. Either you detected a bit when you shouldn't have, or you didn't detect a bit when you should have. So those go out to a little wire, and tracing that down, there's a little connection hidden down here that says A to A prime or A double prime in power connector, right here.
Okay.
And sure enough, those pins do appear as external control signals here. External control A prime, and A double prime.
So the reset wire is external.
It's externally programmed. And the reason you have to do that is that vehicle codes 0 and 7 are both valid. So if you have programmed yourself to be vehicle 0, but you have the error detector wired up to reset the first 3 bits of the bit register
To 0.
every time you get an error, it's going to select the right vehicle, which is not what you want it to do. So they made this also externally programmable, so that if you are vehicle 0, you change that so that it sets the first 3 bits instead of unsetting them. And if you're vehicle 7, you need to change it so that it unsets them instead of setting them.
2 different reset conditions.
Right. For vehicle 4, it's going to be better to reset the bits, because if we set all the bits, then it would only take 2 zeros for us to detect a valid vehicle, because it would shift that default 1 up 2 places. Whereas if we make our default 0, then we have to get all 3 bits correct before.
Yeah. Oh,
It'll
yeah, it depends on which. Ooh.
So it kind of depends on the most significant bit as well.
Yes.
Of your vehicle code.
Gee wee. Okay, so we have to do another wire.
Yeah, that A pin is the subbit error detector. So we're going to be able to see when it picks up subbit errors now, which we couldn't before.
Eric thought about that one. Why don't we choose vehicle 0, and then we can try all the codes. It's 3 times the same bit.
Right.
So we try all the 5 subbits that exist.
Then we can try all combinations, just 32 combinations, and see which one will trigger it. And then we know what it is for a 0.
Yeah.
V is on pin 49, and I put silver circles on all the multiples of 10. So
Okay. And so this one's probably 49,
Yep.
and that would be 50.
So that's our
easy.
our error detect.
Okay.
And then A prime is right next to it.
So
On
51.
Yeah.
There we go. You think we're going to see an error signal?
I hope so.
Me too.
Okay, so you're seeing my bits. Should I send all zeros? What we think is the
All zeros.
pattern for zeros? Tim, there you go. Is that what you see?
Errors.
Errors. All ones. So now we've made further progress. We can try what I think are the correct block 2 subbit codes and see if the UDL thinks they are subbit pattern errors shown as negative pulses in the purple trace at the bottom. No good?
No.
I'm trying the other code for zeros. No. The other code for ones. No. Well, trying the codes from the documentation still did not work, so we are just going to brute force it and try the 32 possible 5-bit codes in succession. Okay, well, let me flip the bits. I'll count. Okay, we start at 0, 0, 0, 0. Alright. Okay. 1, 0, 0. 2. 3.
Well, we're getting something.
3?
Yeah, it's getting us a valid vehicle code now.
Aha. And it's... Wait, that's not it. That's... Oh.
See that?
And that's... I am sending 1 and 3 zeros.
Wait a minute, that does sound familiar. 11000.
Yes.
That's vehicle address, and that corresponds with a 1 from what we decoded looking at what, the schematic I think this was?
Yeah.
So
Okay,
it's-
let me try the opposite of that and see if you can give you a 1. 0 0 1 1 1.
We should get fewer
Do you
error
get something?
pulses. We're getting no valid address, but we're getting no errors.
Yeah, so
Yeah,
this is our 1s and our 0s. But I might be inverted.
I think we might be looking at inverted subbit output here. I think that's what's going on.
Okay, so now you have vehicle address.
Yes. So we have a valid vehicle address.
Woohoo!
Wow, this is great progress.
So this is what I'm seeing coming out of the Updata link box.
Well, it sends
On
the
the
right.
scope.
It sends the
So
right
it was
thing.
sending the right code.
So, wow. So the documentation is wrong, the box is correct.
Correct. Well, and then we had this. The wiring for discovering the address was.
Well, we
was
left out
not
the reset
documented.
address thing.
Yes.
That was the
Yeah,
issue.
nobody told us to put it in, right?
Yeah.
So am I inverted or not there?
My recommendation is to switch over to the non-inverted output
Yeah.
on this generator,
And see.
and then invert your 5 bits, and then that should match up with the code for 0, and match up with getting a 0 out here.
There you go. You get zeros.
Vehicle address selected. Yes, this looks good over here. We're getting this. See, that little pulse there shows that our vehicle's being selected.
So I'm sure you will be thrilled to know that we have finally found the subbit coding of the Apollo Updata link. And the first 30 subbits are encoded using 11000 for ones and 00111 for zeros. And then the rest of the message, which can be pretty long, use a different subbit code, which is 01011 for ones and 10100 for zeros. So putting all this into practice, this is how I coded my messages for abort 1 and clear abort, which are 60 subbit long. And you're probably not thrilled, but we are thrilled. That was a lot of work, and now we can probably remote control the spacecraft once we get the UDL box going, the real Apollo one.
Moments later.
I think I finally managed to send a command to the spacecraft. I wrote it all down, and this should be a message to turn a relay on. And so I have to change this from 5 subbits that did a 1 to 5 subbits that did a 0. Oh! What an achievement! So that is the abort relay. I just sent an abort to the spaceship. And I'm going to turn it off. Don't worry, no problem, everything's fine. There you go.
Easy.
Wow.
That took us like 3 months of work. Actually more than that, because we opened the UDL in June.
Did we?
Yeah.
Wow.
8 months of work.